95% of all reactions in organic chemistry happen because opposite charges attract. Negative charges on one molecule will want to stick to positive charges on another molecule. So let's think about how you can see negative and positive charges on molecules. First, negative charges. You could have a full negative charge. That's easy to see because it'll be written in. You could have a partial negative charge. That's hard to see, but it's very common. It won't be written in. You'll have to see it with your mind. You'll get a partial negative charge when you have bonds between atoms of different electronegativity. So, if you have a bond between a carbon and an oxygen, the oxygen is more electronegative, it'll be slightly negative. If you have a bond between a carbon and a metal, like magnesium, the carbon is more electronegative than the metal, so it steals the electrons, it becomes slightly negative. Now those delta minus charges will not be written in. Those partial negative charges won't be written in. You'd have to see them by seeing differences in electronegativity in a molecule, and they're very common. Another place you can have a lot of negative charges if you have a lone pair. That's just electrons that, even though they're paired with each other, they do have a negative charge and they're open to the outside world. And also if you have a pi bond. So if you have any place where you have pi bonds, you have a lot of electrons in one space. So that's a lot of negative charge in that one space. Okay, let's compare that. Let's think about where you can find positive charges. How would those look in a molecule? Well, you could either have a full positive charge, easy to see because it'll be written in, or you could have a partial positive charge that's harder to see. It will not be written in. You'll have to see that with your mind. And that is intimately tied with the slightly negative charges. These arise because of differences in electronegativity. Atoms that are less electronegative have a slight positive charge. So if we go back to that carbon to oxygen bond that we were talking about, the carbon in that example, the less electronegative element, becomes slightly positive. Or in the carbon to magnesium bond that we were talking about, the magnesium in that bond was less electronegative. That would become slightly positive. So you'd want to see those with your mind when you look at a molecule. Now, because these explain so many reactions, these opposite charges attracting explain so many reactions, like anything that comes back a lot, it has a nickname. Anything that has a negative charge is called a nucleophile. And anything that has a positive charge is called an electrophile. And these are kind of big, clunky names. Let's explain where they're coming from. The phile is coming from the Greek word for love. For example, Philadelphia is a city of brotherly love. Philosophy is the love of wisdom. Philip is a guy who loves horses. So phile is coming from a word to love. And what does a nucleophile love? It loves nuclei. Well, what is in a nucleus? Protons, and therefore positive charge. So something that loves a nucleus would love positive charge. What loves positive charge? Negative charge. So a nucleophile is something that loves positive charge. That's all the stuff that has a negative charge. Similarly, phile again in electrophile is coming from the word to love, but this time it loves electrons. Electrons have a negative charge. What would love negative charge? Positive charge. So first you can see that the names are really telling you that it's the relationships between these that make reactions happen. These aren't just negative charges all by themselves. They're negative charges that fall in love with positive charges. These aren't just positive charges all by themselves. They're positive charges that fall in love with negative charges, and that makes reactions happen. So this is a table that you want to commit to memory and be as comfortable with as you possibly can. Now we're going to use this table to identify nucleophiles and electrophiles in different molecules, and that's what they're asking you to do in exercise 6.8. In this one, they're asking you to identify just all of the nucleophilic centers, not any of the electrophilic centers, just the nucleophilic centers. So we're trying to find negative charge in these molecules. So first, if we look at this molecule here, let's go through this methodically. In A, we do not have any full negative charges. We would notice them because they'd be drawn in. Second, we do have partial negative charges because we have a metal. Metals have very low electronegativity, so they give their electrons away to whatever they're bonded to, and the carbon there will take those electrons and become slightly negative. Notice that when that happens, the lithium becomes slightly positive. So that's our third nucleophilic thing. Do we have any lone pairs? No. Do we have any pi bonds? No. So we've gone through all the possibilities, and we've identified all of the nucleophilic centers in this molecule. It's really just the carbon. And so when this molecule reacts with something, it's going to be that carbon that attacks a positive thing on the other molecule. And notice that I'm going to describe the negative charges, the nucleophiles, as doing attacking. That's because these bonds break and form when electrons move. And the nucleophile is what has the electrons. It's the electrons that act and cause the reaction. And so it's the nucleophile that does the active step. It attacks things. And the electrophiles are attacked. They receive the electrons. Okay, so much for A. Let's go through B. So here, we'll look for first any full negative charges. We don't have those. If we did, they would be written in. Partial negative charges, we do. We have a couple really electronegative elements. The nitrogen is very electronegative, so that pulls electrons to itself and becomes slightly negative. So the atoms around it that it's stealing the electrons from become slightly positive. That's the carbon and the two hydrogens. The other electronegative element we have is oxygen. Remember, electronegativity increases as you go up and to the right on the periodic table. As you go up and to the right, nuclei attract valence electrons more strongly. And so nitrogen, oxygen, fluorine, chlorine, those are even all of the halogens in group 7A. All of those have pretty high electronegativity. They pull stuff to themselves, become slightly negative, and whatever they're bonded to loses those electrons and becomes slightly positive. So you can see that the two nucleophilic centers in this molecule are the nitrogen and the oxygen. Whatever else you know about this molecule, even if you've never seen it, you know that when it reacts with something else, it will be the nitrogen or the oxygen that attacks positive charge on another molecule. And if the molecule does not have positive charge, this molecule will not react with it. Or at least those nitrogens and oxygens would not attack it. All right, we're focusing on the nucleophiles here, but oftentimes when we draw in the nucleophiles, we get to see the electrophiles more clearly too, because of the dipoles that you get. The bonds that have two different ends, the positive ends, slightly positive, and the slightly negative ends, because of differences in electronegativity. So we'll try to identify the nucleophiles in C. And first we're going to look at full negative charge. We don't have that here. If we had it, it would be drawn in. Second, slight negative charge. We do have that. It's on the nitrogen, because nitrogen is really electronegative. Whenever it's in bonds, it steals electrons from the stuff around it. Those things become slightly positive, and the nitrogen becomes slightly negative. Lone pairs. Oh, and I meant to go through this in the previous one too. Lone pairs, that confirms our analysis. The oxygen and the nitrogen had lone pairs, and we didn't have any pi bonds in the previous one. Likewise, in this one, we have a lone pair on the nitrogen. That confirms its status as a nucleophile, and we don't have any pi bonds. So you always want to check all four of these features when you're analyzing a molecule trying to identify nucleophiles and electrophiles. So in this molecule, the nucleophile is the nitrogen. That is what will attack positive charge on other molecules and cause this molecule to react. So one more, let's try to do D. We're going to go through all four patterns. First, let's look for a full negative charge. We don't see that here. That would be easy to see. It would be drawn in. But a partial negative charge, we don't have that here either, because we don't have any big differences in electronegativity, either because of nitrogens, oxygens, fluorines, or in general the halogens, which are very electronegative, or because of metals, which would be have very little electronegativity. So we don't have either of those scenarios, so we don't have those polar bonds where one atom gets more electrons than the other. We don't have any lone pairs, and we do have a pi bond. This is the only nucleophile on that molecule, is the pi bond there. When you mix this with another molecule, it'll be that pi bond that attacks positive charge, and that'll cause the reaction, and that'll allow you to predict where the product will form, or what product will form. If you mix this, notice there's just a nucleophile here. There are no electrophilic centers. So if you mix that with a molecule that only has negative charge, it'll never react with it. So being able to identify these nucleophiles and electrophiles on these molecules is going to allow us to see how molecules, even that you've never seen before, will react. Will react when you mix them. And that ends up being a very profoundly valuable skill to have, to predict the products between molecules that you've never seen before, just based on opposite charges attracting. So make sure you commit this table to memory as soon as possible, and you do some practice identifying those two things in molecules, nucleophiles and electrophiles. Make sure you're comfortable with these terms. So if somebody says nucleophile, you don't have to think, wait a second, was that the positive or the... No, instantly you know that's something that has a negative charge. And electrophiles are things that have positive charge.